begin. Thank you all for coming. We're going to get right started here. My name is Mike Zoeller. I'm a geologist and GIS analyst at the USGS Hawaiian Volcano Observatory. Right now we're operating out of office in Hilo, but for the longest time we were up at the Jagger Museum in the National Park, where so many of the displays here, the Pāhoa Lava Museum, have been sourced from. So this talk today, we're going to talk about some different stuff than a lot of the other Volcano Awareness Month talks that have been, happening the past few weeks across the island, because a lot of these talks have focused on individual eruptions or like a specific aspect of somebody's research. But I'm going to talk a little bit about what goes on behind the scenes when we're doing what's arguably, and this might be my bias as a person who designs maps as my primary job, but arguably our most important job, which is just getting information out about where the lava flows are and where they're going. And so that's why this talk here is titled Multi-Platform Mapping of Active Lava Flows at Hawaiian Volcanoes, because as you're going to see here over the next 45 minutes or so, we use a lot of different techniques to get that information, to collect that information and then disseminate it to the public and get it out to emergency managers and you folks, so that the people of the island can make informed decisions about evacuations, where to go, and just in terms of planning and where we want to live and how we want to develop the island, because obviously the hazards are very different depending on where you live. So just a little bit of brief background on myself. I am not from the island. I'm from New Jersey. I went to college at Franklin and Marshall in Pennsylvania with a specialty in geosciences, and geographic information system was my focus. Geographic information systems are the software that we use to design map products, and we're going to get a little bit into the specifics of that as we go forward here through this talk. So I'm actually going to start with a little bit of history, though, on how we're going to start here with going back to 1983. That's going to be our starting point for how some of the methods that we use today have been developed. And we're going to come through the present day and some of the eruptions that we've had the past few years and how the methods were developed during those events. And then at the very end, we're going to take a little bit of a look at the future and some of the stuff that's coming down the pipeline that might help us even more in the coming years. But going back to 1983, and we're going to start in 1983 because going back earlier than that, I couldn't possibly tell you how they figured this stuff out. It's a miracle that they were able to get accurate data at all, considering that helicopter resources were limited. They had to charter a plane to go fly over these things. But I'm going to start with my area of knowledge, which is kind of like the Pu'u O'o era. Obviously, I am a lot younger. I was not born in I was not around yet in 1983, but I kind of know a little bit about how things were done at that point in time. So when the Pu'u O'o eruption started on the Kilauea East Rift Zone, maybe 20 kilometers uprift of here, back in those days, most of the mapping was done via overflights and helicopters, and then the geologists would come back to the office and sketch what they saw onto these topographic base maps. And they might also take them up in the helicopter with them and just eye different features in that topographic map, like different craters, different little pu'us that they see out there, and just sketch dead reckoning, their best guess of where the edges of those lava flows were relative to those features. And by and large, they were really good at it. Looking back at a lot of this data now with modern satellite imagery, they were right on the money. They did an excellent job, but this was a very time-consuming process. And it worked well for an eruption like the Pu'u O'o eruption, which was out in a remote area of the rift zone. It did affect the Royal Garden subdivision, but the flows would take hours to get from the Pu'u O'o vent down to that area. It was a decent amount of time to react, but sometimes it's not that cozy for us as volcanologists here on the island. As many of you have probably heard, the southwest rift zone in Mauna Loa is a high hazard area where flows can get from the rift zone to the coast in 3 hours, and those are populated areas. So a lot of the techniques that I'm going to talk about here today are things that we're strategizing to help us speed up those timelines and turn their data around faster to get it to the emergency managers, make evacuation decisions, and get it out to the public so that they, if somebody's in the way of a lava flow, that they can hightail it out of there. Over the course of the Pu'u O'o eruption, some different tools came into play, though. So By the end of the Pu'u O'o eruption, this map here is from December 2017, when some of the lava flows were still trickling down onto the coastal plain. Really, the data for the eruption maps was coming from three sources. Helicopter overflights that were doing thermal maps of the flows, and the expert on that is my colleague Matt Patrick, who would carry this thermal camera and like film the lava flow from the helicopter, then georeference all the images and make this like mosaic of all of them that they could then sketch in like the areas that were new flows from that thermal map. Also ground mapping, which is what I'm going to show on this next slide, right? No, sorry, that's on the slide after that one. Ground mapping is just walking along the edges of lava flows with the GPS. Very accurate, but very time consuming. And then the third thing is satellite mapping, and that's something that we still use a lot today. Actually, we still use a lot of number 1 and number 3 today. For the satellite mapping, we are largely reliant on analysts from the mainland, and I'll explain that in just a couple of slides here. But first, I'm going to talk a little bit just about the thermal maps. So this is an example of one of those thermal mosaics that Matt Patrick would have made, and you can see the hot spots in brighter red, and then the colder, older parts of the flows in the blue colors, and then obviously all the gray is just older Pu'u O'o flows. So this is focusing on the episode 61G event that was eruptive just for the last couple of years of the eruption. And so those hotspots that you see here, by and large, correspond with the mapped red, like bright red polygons on this eruption map that you see here. So that second method, the ground mapping, as I explained, was very time consuming, but we got really accurate data. And it looked a lot like this, just somebody with the backpack on, hiking along the edge of the flows. Holding the GPS out over the edge of the flow was probably a little bit unnecessary because the accuracy of the GPS is not actually good enough to make those 2 feet worth it. They could have easily just walked 10 feet over to the side and been well away from the edge of the flow. But that was probably arguably the most fun way to get out there and just experience the lava flow up close and personal and get some really accurate data out of it. But as I'll explain in a moment here, that proved to be a challenge with some of the eruptions that we've had the last couple of years. We weren't able to really do this very much. Now for the satellite mapping, what I wanted to explain further on this is that the reason why this is done by folks on the mainland is that it's mostly using classified military satellite imagery. So there's this group in the USGS called the National Civil Applications Center, or NCAC, and they're based in Reston, Virginia, and they hold security clearances to access like the high-grade military sat images that none of us are allowed to see. So they just hand us this data that came from, they'll hand us like these polygons that have been digitized from the military satellite images, and we just have to trust them. And they're really good at it. They do eruptions all over the world. They've done our eruptions here for about 10 years, dating back into the Pu'u O'o era. So they've become very good at it, but it often does require a little bit of review on our end. Sometimes they might like mistake a wildfire for a lava flow or something, so that's a confusion that we want to remove from the process. But their turnaround is pretty quick too. They can usually get their data from the satellite to our hands in about 6 hours if we're in like a good routine of working through like a consistent eruption. Although it can take a little bit more time to spin up this effort at the beginning of eruption because I think they have to retask the satellites to like view different areas. I don't know many specifics because we're not allowed to know too much more than that. So that was the Pu'u O'o era, and then as many of you know, we transitioned into the Lower East Rift Zone eruption in May 2018 when Pu'u O'o collapsed and the intrusion of magma came underground into the Leilani Estates area. And this was a whole new ballgame because this was an area that we certainly knew that eruptions could happen in, as they did in 1955 and 1960, but it was not an area that we had used any of our modern mapping techniques in before. They were probably doing ground mapping just based on those topographic maps back in the 1950s and 1960s, but now we have all these new aerial tools that we're trying to implement, and that proved a little tricky because here's Fissure 1 on May 3rd, the very beginning of the eruption. Now, how are you going to walk around the edges of this flow with a GPS instrument? It's not going to happen. That's dense jungle down there in Leilani. We tried to do thermal mapping, but it was difficult with all the trees right around the edge of the flows. You don't get like defined edges. And Eventually, we had to resort to some backup options, which was essentially what you're seeing here. So I was back in the office up at the old Jagger Museum for the first couple days of the eruption, and we're trying to get data from the people out in the field, and I start getting pictures like this texted to me, like, okay, so we have a point here for a three-dimensional lava fissure. It's not great, but we can make do with this, and it's enough to get some sort of information out to the public about where these lava flows are affecting the Leilani community, and as a result of data like this coming in, we were able to produce maps like we did in the first few days of the eruptions with just points marking the eruptive fissures. And this was actually not too bad of a depiction. You know, me wanting everything to be perfect, I want to like sketch nice polygons onto the map depicting the extent of the flows, but at the very beginning of that eruption, it was older magma that was stored in the rift zone that was getting erupted, and it stayed very close to the eruptive fissures. So there really wasn't the gigantic lava flow field that we needed to depict on the maps, and just showing the dots for the fissures on a map of this scale was actually fairly adequate. As time went on, and our friends at the NCAC office in Virginia started to get their operations spun up for the Lower East Rift eruption, they did start sending us satellite data, and that was super useful and allowed us to get caught up on those early fissures and allowed us to track the progression of the flows as that eruption unfortunately expanded around the area. So this map from May 30th, this was right when the fissure 8 phase of the eruption was beginning. This is mostly relying on the data that was provided to us from the satellite images, but some of this was also from our sketches onto thermal maps. Worth noting, and I'll show this on a slide a little bit later on, when I'm talking about doing these sketches onto the thermal maps, we're mostly using a software called ArcGIS Pro and formerly ArcMap, which is a geographic information system software where you can load in like a base map image, whether it's an older satellite image or if it's like a new thermal map, and it's geo-referenced in three-dimensional space. It knows where to place that map on the globe. And from that, we can then go in and click and like put lines in there and polygons like depicting the bounds of that lava flow, and then use that data in a map like this, which is a more generalized depiction. It's not quite as confusing as like looking at a satellite image. We did also rely a fair bit on drone mapping during the 2018 eruption, and at least early in the event, we were relying a lot on the Hilo Spatial Data Analysis and Visualization Lab run by Ryan Perroy. He and his students were out here most of the evenings flying their drones over the flows. Later in the eruption, we had a whole crew of USGS folks come out and start to assist with that mapping. But you can kind of see here from this map what part of the problem with the drones was, because these little sketches on here are the flight areas that they were able to cover, at least Ryan Perroy's group during that eruption. And it's very small and confined to the vicinity of the fissures. So when you have a fairly large lava flow field, and I think it was 35 square kilometers, the whole 2018 eruptive fissure system, the drones are a little bit limited on their range. They can't quite get out to the full extent of that. And so most of the drone work during that eruption was focused on the fissures themselves, not the distal ends of the lava flow. Although there was a little bit of work up at done up at the Four Corners area where they were able to access some of the flows that were extending towards the vacation land subdivision at that time. Next, I'm going to talk a little bit about how we were disseminating this data at the time and getting it out, getting the word out. So we obviously are producing those static maps that just go up to the HVO website as JPEGs or PNGs. But we were also, at the time of the 2018 eruption, trying to provide a more dynamic depiction of the data in an online map. And the way we did it at that time is that we had this ScienceBase page. ScienceBase is a USGS catalog of all the data that we're putting out. And we had a ScienceBase page for a preliminary map of the 2018 Lower East Rift Zone eruption. And this allowed folks to go in and browse the data on a different base map of their choice. But this proved to be a little bit clunky for us on the upload end. Like, we had to rewrite the data in there every time that we did this. And especially during Mauna Loa, just back in 2022, we improved upon this a lot, and we developed something that's a lot more streamlined for us and easier for the public to use, and I'll talk about that in a little bit. After the 2018 eruption ended, we had 2019, the year of no lava, as it'll probably become known eventually, and it was a chance for us to breathe at HVO, but also we did do some really important work in that we contracted a LiDAR survey. LiDAR is light detection and ranging, where in this case, a helicopter flew over the Kilauea summit, the Pu'u O'o flows, and the lower east rift zone flows down here with a laser scanner and produced an extremely high resolution 3D model of all of those areas. So we got accurate, from that we were able to get accurate elevation data of the flows and get like the volume change, well, the ground surface change from before the eruption and then thus the volume that was erupted. Up at the summit, we were able to model the collapse crater, which was shortly thereafter filled in by the water lake in 2019. This proved to be foundational for so much of the work that has come in succession in the past few years. Having this high resolution data allowed us to do extremely accurate measurements of the lava volume erupted up at the summit eruptions, and has allowed us to incorporate this updated topography both at the middle east rift zone and the lower east rift zone into our DEMs of the whole island, and to use that for flow model simulations, so that if an eruption happens in these areas again, we're not using the old topography to model the directions of those flows. We're using the new and the latest and greatest new stuff. And as I explained, that data, especially up at the summit, was really useful once we started having those summit eruptions. And when those first started, and this map is from the very beginning of the second summit eruption that started September 29th of 2021. In this case, I didn't even wait for like a helicopter overflight or anything to make this map. We had such good webcam views of the crater, and we had folks on the crater rim shooting vertical distances with a laser rangefinder down to the new surface of lava down there. We knew within like a vertical meter exactly the level that the lava was at. And just based on like drawing a contour line on that LiDAR digital elevation model that we got in 2019, we were able to get like the exact bounds of the lava flow on the crater floor and get the exact volume that had been erupted. And also just like jotting in like the positions of the fissures, and that's kind of just triangulation from the webcams. Like, you know, looking at it from one angle, seeing that it's like, oh, it's just to the east side of that island that's there in the middle of the crater. And then looking at another view and seeing like, oh, it's actually a little bit more off the north end. So kind of just like pinpointing them in from that. And this is kind of like a rough and dirty way to do it at the very beginning of the eruption, get the information out there as quickly as possible. As these summit eruptions have progressed, we're able to dive into more analytical and more detailed methods. And so this is an example of a structure from motion model that we generated from the second Kilauea summit eruption, in this case in March of 2022. Structure from motion will fly around the crater in like an orbital flight path, whether it's in the helicopter or in this case with a drone, take a bunch of sequential images, and then using this software called Agisoft Metashape, we can merge them all together and create a three-dimensional model and an orthomosaic of the area, you know, depicting, you know, the colors as well. And so this is a slightly more accurate method than what I was describing on the last slide, just shooting the distance to the lava on the crater floor, because with that surface is not always exactly flat. There is a little bit of relief to it, maybe as much as 10 meters or so, because the lava will often bulge on the side where it's coming into the lava lake from. So it's a little bit higher in that spot, and we can get a slightly more accurate depiction of that topography, the extent, and more accurate measurement of the volume from a model like this, and comparing to the previous ones that we've done. So we were doing these, whether it was from the helicopter or from the drone, maybe like once every week to 2 weeks during that eruption. That second eruption lasted over a year, and we got into a pretty good rhythm of doing them really routinely. Got a little bit more challenging with the last couple of summit eruptions just because they were so short. We weren't able to spin up the drone and helicopter monitoring helicopter mapping quite as much, and it was a little bit challenging with the wider geometry as well. A little bit far for the drone to cover, and also the helicopter, we couldn't fly on the downwind side. You know, we'd be clouded out in the gas, so we're kind of confined to those north and east sides of the crater that were upwind, and which is not as optimal for the viewing geometry, but we were able to make it work at least on a few occasions to get decent data. So this is an example of one of those digital elevation models that came out of those structure from motion surveys. So we're looking here on the west side of Halemaumau crater with the most recent lava filling in that western basin of the crater, whereas the most recent eruption at Kilauea summit was actually over on that downdrop block over on the right on the east side of the crater. And from this data, we're able to, of course, produce the accurate eruption maps with the statistics, like you see here on the bottom, that a lot of people like to use to track the eruption. So we have, usually on these, we're providing a number for the crater floor, but there's usually a volume averaged level. It's not like the highest or the lowest point on the new lava. It's kind of just an average of the whole area from this eruption. And we're showing the rise, and that lava volume is a differencing of the model from this particular date versus the one from right before that eruption. So when an eruption ends, we get out there with our highest detail cameras and get like a really, really good model, because we know that we're going to need to tie in the further surveys to that non-eruptive model to get the difference in volume and difference in elevation. So that was the Kilauea summit, which proved to be a very, dare I say, easy eruption to map. You know, being confined there in the crater, everything was kind of right there in front of us with the webcams, and you know, for those of us visiting on the ground out there as geologists. Then we had another eruption in November of 2022 that you might have heard about up on Mauna Loa, the largest volcano on the island and largest active volcano in the world. This is a webcam image from right at the start of the eruption. I was unfortunately asleep when it started. I missed the fun stuff at the very beginning, but as soon as I woke up that next morning very early, it was kicking into high gear to try to figure out where those lava flows were going. We had vague views from our webcams, but it was very tricky to pinpoint. And further complicating matters, the weather was really, really poor that night. I don't know if you folks remember, if you were here on the island at the time. The summit was clouded in, and this was actually one of only a few frames that the thermal webcam was able to see the lava, because the clouds just came right back in and clouded over and blocked the views. And as an example of that, this is one of the only satellite image that I'm going to show today, because this is a commercial Sentinel-2 image. This is not one of the classified ones. And so this is what our analysts back on the mainland were trying to work with in delineating these flows. And so you see some red peeking out through the clouds there, but that's actually just the lava channels. We're trying to get the whole extent of the flows that's been inundated. So this wasn't super helpful at the time, and it was not. We were still hopeful that the satellites would be able to provide us with some useful data, but at least in those first couple of days, we were kind of blind with the satellites, and we had to resort to some other methods. Let me just get a little bit of water here. So that first full day of the eruption, starting with the morning of November 28th, 2022, we were able to get up with our helicopter observations, which we've relied on for so long here at HVO to observe these eruptions. And I was lucky enough to be on that very first overflight. And one of the issues that we had kind of predicted in advance of monitoring these Mauna Loa eruptions is that how are we going to convey positions from somebody who's up in the helicopter for hours on end back to the folks in the office who need to know this information and get it to civil defense as fast as they possibly can, to let them know what inundation zone on Mauna Loa the lava might be going into. So we kind of predicted that this would be an issue ahead of time, but fortunately, I had done a little bit of gaming this situation out in advance of the eruption, just just as part of general prep, like eruption prep work. And we had developed this, this mobile app map in ArcGIS Online and using an app on an iPhone called ArcGIS Collector, which has now been renamed Field Maps. And we had it pre-populated with satellite images as background, topographic maps, and then a bunch of empty layers, as we call them, which is just like polygons or points or lines that you can put features into the map. And we had empty layers for lava flow polygons, lava flow margins, eruptive fissures, flow front points. And so I'm up in the helicopter and I'm realizing like, this is exactly what I designed that thing for. And so I pulled out my phone on the helicopter, started jotting in lines just for the eruptive fissures, just based on like my position in the helicopter, looking over at this eruptive fissure. It's starting at this one Pu'u, it's ending at this other Kipuka, like maybe a kilometer down the rift zone, and just jotting these lines in and then plotting the flow front points as well, based on sometimes laser rangefinder measurements, or if we were able to like fly right over the front of it, I was able to like drop a point in the map. And so I was able to like get on the radio and just say like, hey folks, like back at HBO in the office, like open the map up, like the data's there. And so within an hour, they were already running flow model simulations to see where the flows might come down slope from that. And it was even from like those early hours of the eruption, it was clear that it might be going towards Saddle Road. Fortunately, it stopped before it got there, but we could kind of see that was the direction that the eruption was going to take, just based on that initial data. Because if we get nothing else up there, as long as we get where the eruptive fissure is, where the lava is coming out of the ground, we can run those topographic simulations to see where the fluid is going to travel down slope. So we can operate with even like a small amount of data to make some pretty educated guesses about where things are going to go. So from that data that was collected up in the helicopter, we were able to produce the first map of the eruption that afternoon of November 28th, showing just the fissure, the flow front points. And then on this map, I put in these labels up at the summit and like on this like upper southwest flank, and then on the upper part of the northeast rift zone, just saying like, we know there were fissures here. Like we flew by them in the helicopter, we could see them, but we only had partial views. Like it was not going to be possible to go in and digitize those whole bounds in the time that we needed to turn around this map. Like the most important thing, as I said, was where the fissure was, where the flow front points were, and for our analysts to start figuring out where that might go if it continued down slope. As time went on, we did eventually backfill some of that data, mostly using satellite images, which I'll show the rest of that data in a moment. But as things started to encroach on Saddle Road, we also started to resort to some other novel techniques, which is pretty simple, just shooting distances using our laser rangefinder. We use a Vector 23 laser rangefinder that can shoot distances up to like 40 kilometers. So the flow to Saddle Road, I think, was 3 kilometers at the closest, so it was well within range. This instrument is extremely expensive because they're actually made for sighting military artillery, but we have 2 of them, and they've been used to great advantage at the Kilauea summit and during the Mauna Loa eruption here. But the problem with that is that although you get extremely accurate data, and we got that critical information of how far the lava flow was from the road, which is what civil defense was so worried about, and understandably, because that would be a major artery for the island cutoff. That's only providing us with a point for the front. We want a little bit more comprehensive data, showing the full bounds of the flow. And so while our satellite analysts were still catching up because the weather was still bad for the first couple days of the eruption, another novel technique that we developed was just webcam mapping of the flows. So I talked a little bit about this with the Kilauea eruptions, how we were able to kind of triangulate, but this was, I thought, even more innovative, because you look at this webcam view. This is from our MK cam up on Mauna Kea, which looks back at the north flank of Mauna Loa, and that flow coming down. This is, I don't have the date on here. I think this is like November 30th or so, maybe like 2 days into the Mauna Loa eruption. You look at this in the dark, and you have no reference points. It's like, where is this thing in space? But fortunately, because that camera is fixed, we know that the daytime views are exactly the same extent as what you're seeing there. And so we can just jot in a line for where the flow front is on the dark image, transpose it onto the daytime image, and then by comparing to other features that are visible in that daytime webcam image, we can sketch it in relative to them. So in this image, take note, very faint, there's a little lighter colored kipuka of extremely old lava, maybe like 4,000 to 5,000 years, right off the tip of that flow. And as I toggle to this next slide, oops, went too ahead. That is this right here. So looking at this image on the pixel level and picking out extremely fine scale features like that in the webcam image, and if you know what you're looking at and can orient your brain correctly to this satellite image, which north is up here, so we're looking back in the opposite direction now, you can pretty well locate. This is not as accurate as our other methods, but I think we were probably within like 100 to 200 meters on the ground in terms of accuracy of the position of this flow front. And when there's no other data available, this is what we work with. And I think we did pretty well with this method during Mauna Loa, and if we have to rely on it again, then I think it's well refined and it's reasonably accurate at this point. So this is an example of the map that came out of that particular effort to do that webcam mapping. So you actually see a combination here of, this is the red polygon is what we sketched in from the webcam image, and then we actually put an extra dot on there because the flow had moved a little bit in the time that it took to do that work, and somebody at the Saddle Roads shot a measurement with the laser rangefinder. So we showed like an extra point to just say like, okay, it moved like another couple hundred meters closer to the road. And then this was also the point in time when that other flow was active from fissure 4. So fissure 3 was the main fissure of the Mauna Loa eruption. Then we have fissure 4 coming down and send another flow that eventually crossed the observatory road. We were also able to pinpoint the front of that with reasonable accuracy from the webcam images. But right at the end of the eruption, we started doing something even more exciting with the mobile app that we were using to transmit this geospatial data back to the office. Because we realized that we have a good cell service up there. We can leverage this even better by using also our extremely skilled helicopter pilot, David Okita, to actually fly along the edges of the flows, not directly on top of it for safety reasons, but offset by maybe 20 to 30 meters. Just fly along the edge of that and then have somebody recording in the ArcGIS collector app while the helicopter is flying along, input that data immediately into this cloud map in ArcGIS Online, which was immediately visible to me in the office and to Civil Defense. We were able to open up the sharing on this so that Civil Defense could see the data right away. This was really nice because it was reasonably accurate, and it required no extra cleanup from myself and the other GIS analysts to present data to the Civil Defense folks. They could see it as it was being collected, and they were really excited by this, and I think we're going to be using this method a lot in the future. Now, we don't typically show these on our public maps though. Like, we need to go in and do a little bit of cleanup in order to make this look pretty and make it a more realistic depiction of the flow, because we're depicting a 3-dimensional feature here. We can live with 2-dimensional polygons, but lines for the edges are not the greatest, so we want to do better than that. And that's why we have a workflow to go through the processing of that data and get it out in such shape that it's depictable on public maps. And so this workflow that I've charted out here, you kind of think of these as 3 different methods, each of these columns. That one that I was describing most recently with the field data being collected by the folks in the helicopter, that's this first column here. So they're collecting the data in the ArcGIS collector app, and it's immediately visible to the Civil Defense folks. But even so, myself or one of the other GIS analysts will clean it up, populate it into the polygons layer, which we call flow polys, which is also visible to civil defense. And then somebody will review it, just to, somebody who's been out at the flow that day, just to say whether or not that makes sense and whether or not we can put it on the public map. They give the sign off, then we just toggle a button and it goes under our public map. And once it gets to this stage, we'll usually make one of the static maps, and as I'll describe in a moment, it will go into the dynamic map that's visible online and available to the public. Now, the other two methods are, I'll jump to the third column here, the satellite imagery. So folks on the mainland are analyzing that. They'll typically provide us with lines or polygons that require a little bit of cleanup to fit with the older stuff that was previously mapped during the eruption. Then we'll populate it into the polygon layer. There'll be another review by a local expert, and then we toggle permissions to make it go out to the public. This might sound like a lot of steps, but all in all, this only takes like a couple hours at the most. Like, it's a pretty rapid process, but the fastest way to do it is that we do it ourselves, where we analyze our thermal images, or if it's a webcam image, and myself or one of the other GIS analysts populates it into the flow polys layer. And because we know that's the best data available and we are the experts, like who's going to review stuff that like I put in, because that's the best it's going to get, we just kick it straight out to the public immediately. So that's the fastest, but because of some of the deficiencies of those methods, it may not be the most accurate positionally. It's good enough for the scale of the maps that we're providing, but we're also trying to build data sets that we can publish after the eruption. So we're trying to keep that in mind as we're going along with this, and trying to make as reasonable a database as possible for us to put out to the public after the eruption's over. So during the Mauna Loa eruption, we were putting this data into ArcGIS Online, but we, USGS, did not have our system set up to put our flow layers out to the public. But fortunately, Civil Defense did. So what essentially, Asia Wasser, the GIS manager for the county, she just replicated our data and put it out into the county's ArcGIS maps. And so it was visible to everybody there as soon as we were putting it in. And so we were extremely thankful to the county for making that available to us, that they were able to replicate our data in that way. But in the future, we should be able to, in addition to doing that, we should be able to host it on our own as well. Because we've kind of ironed out the workflow for us to make our own data public. And in a big eruption response like Mauna Loa, or something like the Lower East Rift Zone ever happened again, we should be able to put out our own ArcGIS Online map that the public can access, and which would also be replicated to the map on the HVO website, hosted in the exact same way that the historical flow polygons are hosted on the HVO website map right now. So it would just be another layer in that map that you could toggle on and off to see the most recent eruption data. Probably as like the bright red polygon for the most recent part of the flow, and then like the pinks for the older stuff, which is kind of like the classic color scheme that we've used. One of the other tools, though, that I've also been working on, and we have been working on at the Hawaiian Volcano Observatory to further speed up the alerting, is further leveraging our webcam network. Because as I was describing to you guys, like those nighttime views can be very tricky to pick out positions of things. And potentially our most useful camera for this is the new webcam that has been put on the Kīlauea volcano just in the past year or so, looking back at Mauna Loa. This is a pan-tilt zoom camera, so we can change the view around, but we keep it on this default view looking at the summit and upper southwest rift zone, because this is the area of probably greatest concern to us on Mauna Loa, because flows that come out of the summit are probably going to stay pretty close to there. Flows on the northeast rift zone are going to impact like not very inhabited areas, because it's mostly state forest reserve up there on the Mauna Loa northeast rift zone and national park land. But the southwest rift zone, it doesn't take very far for fissures to propagate before they can start going down slope and start affecting South Kona and the communities down there. So we're taking a very close look at this area, and to help us do that a little bit better, we've developed these webcam overlays, where we have specific landmarks pinpointed in the image and visible to us on our internal network. These are unfortunately not available to the public yet. Maybe someday we'll be able to get them out. The reason for that is because it's a pan-tilt zoom camera, the view might change. We have to do verification that the view is looking at the right area in order to put the overlay on there. But I'll give you an example of a situation where this would be super useful, because this is the view of that camera at night. And if I took a little bit of liberty with this next slide here of a semi-ridiculous depiction of what a lava flow might look like on this camera. So you look at that, and kind of like that one I was showing you of the Mauna Kea camera, you can't position like where is that fume coming out of the volcano in three-dimensional space. Like it's a huge volcano, and with no landmarks in view there, it's very hard to pinpoint that. But you put the overlay back on from the daytime view. So making these overlays, I go in and I sketch all the features in like the daytime image, and I also put the lava inundation zones on here. So these are like, this was a published map a few years ago showing like the different sectors of the volcano that the lava can come out to. Not to be confused with the lava hazard zones, because these are more like watersheds of like the different drainages, so to speak, that the lava can get captured in and take it down to the coast. So in this mock-up I've made, you see that the eruption has started at the summit, which is the typical pattern for Mauna Loa. But then as we progress here, we start having a fissure coming down to the southwest, but not so fast. That actually happened during the most recent eruption, where a fissure propagated just a little bit out the southwest side of the caldera and sent flows within just a couple kilometers of the vents. But it didn't go any further than that. It then reversed back to the northeast. And this is actually a pretty common pattern with Mauna Loa eruptions, that it kind of starts going to the southwest and then doubles back to the northeast rift zone. Same exact thing happened in 1984. So we weren't terribly surprised by this, but it's something to watch out for, because it's really if the flows start propagating further down the southwest rift zone, like if they get to Sulphur Cone or this other location called Dandelion, where we have our M3 camera further out on the southwest rift zone, that's a good indication that it's a true southwest rift eruption, and we got to start thinking about taking action in South Kona. So just as an example of that, yeah, you're just my crazy drawing of an eruptive plume coming out there just downrift of Sulphur Cone. So that's an example of what we're looking at with like a true southwest rift zone eruption. And we could also turn this camera and follow the flows as they come down to the coast. This pan-tilt zoom has a full 360-degree span of view, and you can even see like Milili'i and the coastline in South Kona and Kau from this camera. So that's it for the GIS portion of this talk, but I'm just going to close with a couple slides just updating everybody on what's going on with each of the volcanoes. We spent so much time on Mauna Loa at the end of this talk. Since the end of the 2022 eruption, seismicity has been very low, so we like to see that, but worth noting that the rates of deformation are still kind of high. Their GPS instruments are showing that the summit caldera is still expanding a bit. That's not terribly unsurprising, because a similar pattern was observed after the 1984 eruption, where you evacuate all this shallow magma from the summit reservoir coming to the surface as lava during the eruption, and then the deeper parts of the reservoir system kind of like backfill that pressure. So you get a bit of inflation afterwards, and you can see there that the rate is still tailing off a little bit, but we're seeing rates higher than at any period before the eruption still. So we're still keeping a close eye on Mauna Loa, although no eruption appears imminent right now, thankfully. And then there's our other friends here, Kilauea. Good news for all of us down here in Lower Puna is that most of the activity has been centered up around the summit. So we've obviously had the 5 summit eruptions since 2020, and since the most recent one ended in September of 2023, we've seen a lot of seismicity out on the southwest rift zone, specifically in these 2 areas, the southwest rift connector and this little cluster out by the Kamaki'ia Hills in the middle southwest rift zone. And we've seen some activity in the upper east rift connector kind of the areas between Mauna Ulu and the summit caldera, still with some seismicity below the caldera as well. So we're keeping an eye on this. We saw similar patterns of seismicity outside the caldera region before a couple of the other summit eruptions. So seeing seismicity in these areas is not necessarily an indication that things are moving imminently to the rift zone. Just because it's an active volcano, eventually that's going to happen some point down the road, but nothing from this is a direct indication that that's imminent, that we're looking at a rift eruption. And fortunately out here in the middle and lower east rift zones, seismicity has been very low and there's not much evidence of dilation of the rift zone either. So there's right now it's all quiet on the eastern front, so to speak, of Kilauea. That's it. I'm going to pull up this last slide, just highlighting a couple of the other talks. Tomorrow, Liz Gallant, University of Hawaii at Hilo professor, is giving a guided hike out at Mauna Ulu, and then we got a couple other talks coming next week to close out Volcano Awareness Month. So I'm happy to take any questions. I think I timed this pretty well. That was 47 minutes, so we got a few minutes left for questions. Thank you guys for coming. Yeah. What's up?
I'm curious if there's a connection between calculating the volume of lava that's in the crater and modeling the flow and perhaps even incorporating like the viscosity, I don't know if it's the right term, of the lava to predict where it's going to go and how much.
Are you talking, when you just a point of clarification, when you say the volume of lava in the crater, are you talking in the magma chamber, or are you talking about in like the lava lake that's like sitting up there at the surface at the summit?
The lava lake, if I understand the Kilauea eruption, it actually collapsed because the
Oh, okay. Yeah, so yeah, especially in the case of the 2018 eruption, the volume of lava that was erupted out here on the rift zone and the amount of collapse that occurred up at the summit was almost exactly the same volume. But we didn't necessarily know that at the time because we weren't getting the accurate modeling of the summit collapse volume while the eruption was going on. We were only able to like tie that in perfectly once the eruption ended. But you are right that tracking that volume is really important because it's an indication of how much the reservoir, so like the magma chamber below the summit, a couple kilometers down, how much lava has left from that, and how much we might expect to remain in it, how much it might refill after the eruption. So quantifying that erupted volume is very important for understanding the dynamics of what's going on in the magma chamber. Hopefully that answered your question.
So related to tools used for mapping,
Yeah.
there are some that are consistently in place, like webcams,
Yep.
satellites. But what is the timeline to get someone from USGS into a helicopter and to a site?
Well, if it's daytime, it's pretty fast. So like we have a good rapport with our helicopter pilots that like if an eruption happened in the middle of the day, like they'd hustle us out there within like an hour or so in all likelihood. But if it happens in the middle of the night, we can't fly at night. We're working on some things with the military that we might be able to leverage some Department of Defense assets to go up and look at it. There's also, well, just the expansion of the webcam network. We have plans to put more cameras out there, especially on Mauna Loa on the Southwest Rift Zone, to see it up close, and that helps mitigate the weather issue a little bit more when you just put cameras up there, almost essentially as like tripwires, you know, just canvas the whole thing and see up close where the lava's coming. So it can be very good, but it can be very bad, essentially, our response time in terms of getting aerial views. Yeah.
If I can,
Yeah.
my relation, because you did mention the number of webcams
Yeah.
that are put in place. A place like Pu'u O'o in the park is considered by many Hawaiians a sacred space.
Mm-hmm.
So is there a limit to the number of webcams? Has that already been established between USGS and practitioners?
There's no hard cap. It's more of like a situational review. So just as an example, we're thinking of putting this is not Ue Kahuna, but there's a cone up on the Mauna Loa Southwest Rift Zone called Dandelion, where we're thinking of moving our camera to a higher spot. And we're not subject to any quota in terms of the number of cameras, but the park has asked us to take one of their archaeologists out to see if there's any evidence of like of Hawaiian habitation up there that we don't want to interfere with. So it's a situational thing like that, and there are certain areas where we have a little bit more freedom, where there's not as much cultural sensitivity or opportunity to interfere with cultural relics. So we're able to deploy cameras a little bit easier, but we have a good working relationship with them too, and they've made our lives very easy in terms of the permitting process and turning things around quickly when these eruptions happen. Yeah.
Yeah, do you see the potential use for side aperture radar at all, either airborne or space-based, especially on Mauna Loa where there's a lot of cloud cover and you want to try to cut through that?
We do use that a lot. Mostly our geodesists actually. They'll use it for like centimeter scale measurements of like ground swelling to indicate whether or not like the magma chamber is expanding. We haven't leveraged it as much for tracking the lava flows, but we did start a little bit with that during Mauna Loa, where essentially what the geodesists would call noise, the areas that were like completely decoupled the ground surfaces, like that's a good indication that lava came into that area because the surface looks nothing like it did like in the last scan before the eruption. Was that what you were going to say, Katie?
Yeah. That was used actually to map those kind of southern Caldera initially during Mauna Loa because we hadn't done any overflights, and so they used that differencing to outline those.
Yep.
And that was satellite-based or airborne?
Satellite. Yeah, I don't think we've done any like helicopter plane aperture radar, but yeah, we definitely do satellite stuff. Yeah.
And we experimented with a tripod-based radar as well. Liz Golan, who's now professor.
That's right. Yeah.
Experimented with it.
You need something, Dane? Sorry.
Ask a question.
Oh, okay.
So we were asking everybody to try and repeat the questions, but I'm going to try and use this microphone to see if we can maybe get away from it. But I have two questions for you, really. First one was the map you were talking about for HVO and USGS when you're going to be able to share these lava flow layers when you get released. Will those include a download option for KML or KMZ? Hopefully. All right, that'd be great. And the second question, on the mock-up that you did with the template over from Hualai up onto Mauna Loa, did you do that in MS Paint, that mock-up?
No, I did use Adobe Illustrator.
Okay.
I just have to do a quick PSA. My name's Amadeo Markov. I'm one of the founders of the museum here. I just wanted to ask everyone to please sign in before you leave. Give us your name and your email. It helps us track the number of folks that are in here and whatnot. And this is a nonprofit and we're donation driven, so if you feel like making a contribution, we'd be really thankful. Thank you so much.
Thank you guys for hosting us. Yeah, great. Yeah. If there are no other, one more question? Okay. Well, I guess we'll wrap up then. But feel free to ask any other questions privately offline while Katie and I are breaking down here. So thank you guys again for coming. Yeah.